Geology teaches us that our world is constantly changing, but the process is often so slow that it is virtually invisible. Rapid changes are taking place now in Alaska's Arctic, and National Park Service scientists are working to understand the phenomena of melting permafrost and the impact it will have on one of the world's most delicate ecosystems.
So I'm Dave Swanson. I'm an ecologist with the National Park Service, the Arctic Inventory and Monitoring Network. And one of my responsibilities is monitoring permafrost. And as a part of the permafrost vital sign monitoring, we are monitoring the state of a number of large erosion features that have formed in the Arctic Network National Parks as a result of thaw of permafrost. So permafrost landscapes are, they can be quite dynamic because they have ice in the ground, which is, of course, thaws if it gets warm enough, which it does every summer. And that can lead to a variety of things, one of which is known as thermokarst, which is a process by which the land subsides and collapses because of ice thawing underground. And this is the kind of thing that's happened forever in permafrost terrain. But of course there's concern that as the climate warms that it could become more prevalent. So the features that we are particularly interested in monitoring in the Arctic Network are one of these more dramatic thermokarst features known as retrogressive thaw slumps. And these are large amphitheater-shaped features where the permafrost is exposed in a big cut bank on the upper end of it, and as the permafrost thaws, the material falls off of this face, and then it lands at the bottom and forming this sort of muddy zone, very unstable, wet slurry of material that forms below the permafrost thaw zone, and then that slides down the hill out of this amphitheater and potentially into a nearby river or lake. So I think that what we got here is, you can see the modern soil layer here. It's kind of dark, a little moss and some vegetation. And then this is glacial till. It's frozen. Permafrost probably never thaws more than about this far down, except now it's exposed. And then we go down, and this layer down here is real dirty ice. It's probably 80% water. So anyway, and the way this thing then grows is by this real ice-rich layer. As it thaws, it undermines this bank here, and then the soil in this bank falls down, and it's thawing too. And then the whole thing gets transported down. We got kind of a slope, enough of a slope here that it can all ooze downhill on top of the mud. We're interested in seeing how these slumps grow over time, and we'd like to develop a time series showing, year after year, how fast do they grow, how big are they getting, when do they stop, that sort of thing. And the way we're doing that is we're creating three-dimensional models of these slumps using a combination of aerial photography and ground survey. In order to give us a scale on our 3D pictures that we're going to create by shooting out of the helicopter, we need to survey in some exact dimensions on the ground. So we set up this highly accurate survey equipment here, because it's called a total station. It's used by surveyors and for things like construction sites and that sort of thing. And so we set that up at a place, and we get a good GPS location for the location of the tripod to set us somewhere in the world. GPS isn't quite accurate enough, I don't think, for the dimensions we want of our object, so we're not going to try to GPS all of our control points. We're going to use the total station, and so we place these aerial targets out on the ground, and then one of the workers here takes this rod out, and we shoot a little beam out of the total station to this target as it stands on one of those X's that can be seen from the airplane, and we can determine exactly where that X is in space. We get a right down to the millimeter actually in distance from this one. Then we get back in the aircraft and fly around the thing, shooting numerous overlapping aerial photographs of the slump. And then we take those pictures back to the office, and we have some really snazzy computer software that can take the coordinates of those X's that show up in the picture, and the change in perspective that you get with each of these overlapping photographs, and from that it can create a three-dimensional model of the slumps, including all the topography and with the photograph draped over it. And we can do that, and then we can return the following year and shoot the pictures again. And the second time, we don't need to do the survey over again. We actually can just match landmarks to make the new model line up with the old one. And we can return year after year and just fly these overlapping photographs and use the software to create a new model, which we line up with the old model. And then we can document how fast these things are growing and how much material is being shed down into the lake nearby or whatever that might be. After a thaw slump occurs, you have an extensive area of bare soil. And there's colonizing vegetation that can do a decent job of covering that thing over in 10 or 20 years. At least if there isn't continuing erosion, which sometimes occurs, like if a water course happens to be running down the thing. So in a decade or two, you can have decent revegetation of the thaw slump, but it'll be revegetated, but it doesn't look like the vegetation around it. So for many decades later, you're still able to recognize an old thaw slump. So we're seeing thaw slumps that are 30, 40, 50 years old probably. We can still see the outline of it on the air photos. And I imagine it's going to be centuries before a thaw slump would be unrecognizable by vegetation. Because what happens in the Arctic, there's a layer of organic matter that carpets the landscape really in any place that isn't too rocky and dry. Once that layer takes centuries to develop, and different vegetation grows in that organic layer as opposed to in a bare soil where that layer is missing. And when you have one of these big thermokarst thaw slumps, you destroy that organic layer and different kinds of plants come in. Typically shrubs, large shrubs and more grasses and that sort of thing will come in. And it may take centuries for that organic matter to build back up so that it resembles the undisturbed tundra around it, which is typically dominated by sedges and plants that really thrive in that organic layer.
Thermokarst activity in Alaska's Arctic is a dramatic reminder that our knowledge of the dynamic processes that form our world are far from complete. National Park Service research is helping to build our understanding of the complex interrelationships between climate, geology, and nature in the living laboratory of America's greatest remaining wilderness.